Wonderful. Hello, everyone. Hope we're all having a good Tuesday. My name is Arya. I'll be your lecturer. I mean, that's kind of common knowledge now. I've been the lecturer for the past 2 weeks. I understand, of course, there's a lot of excitement going on outside as well with the fireworks for a happy Lunar New Year. So there's going to be excitement outside and inside because we're now going to be covering classification today, the other side of supervised machine learning. I think it's poignant first to have a quick 5-minute recap over our last session, which was advanced linear regression. Advanced linear regression, we instead actually looked at having multiple features being put through the function with their own individual weights to achieve one output, one continuous output on a regression. So we adapted our linear regression function to have a weight and a feature input for each feature we wish to include. Bias and the weight and the input retain the same like letters algebraically. And we looked at how vector multiplication works and what a vector is in general. For a quick refresher, a vector in the context of computer science describes a one-dimensional array. So with vector multiplication, it works how it would in mathematics, where the first elements of each vector get multiplied, then the second of each, then the third of each. So we can actually simplify down this equation to vector multiplication between each weight and each feature. So we looked at the different ways in which we can capture vectorization, the most efficient being through NP dot, which does it all in parallel as opposed to through a loop. And it's in terms of computers, in the scheme of computer science, it's actually very important that we have efficient running programs. As with parallelism in play, we can turn a 5-minute task that one processor will take up into a 1-minute task that 5 processors will take up, which is very, very efficient. But before we continue to this next section, classification, we actually have a little game. Thomas?
So actually we have like a small activity here. So, and from this activity, we're gonna show you guys like a real world example of like collecting data and then build a linear regression model out of it. Just give me a few moments to set this up. Yeah, so for each table, can we have like one volunteer, like for each table, just to throw some darts? It's pretty fun, so give it a shot. Oh, we got the first volunteer. Yeah. Yeah.
Dart?
Yeah. Wait. Yeah. If you can make like a line here, that'd be great. Oh, so for you, can you stand like up around 1 meter?
1 meter.
Yeah,
Okay.
like
Let's think 1 meter.
yeah, yeah,
Like
just
that,
about that. Yeah. And
Okay.
can you show? Wait, record. There's that. Yeah.
Okay.
Just try your best. Oh, that's about like 50, I think. Oh, you want to try again?
Yeah, can I?
Yeah, for sure. Yeah, it's kind of like sliding. Yeah, sure. Oh, that's like 50. Yeah, 50. Yeah. Can you also stand like 1 meter away, like around here? Yeah, that's probably.
There you go. That's the line.
Yeah, that's a line. Yeah. Like 40. Want another try? Yeah, around here, I think. Yeah. Ooh, 60. Okay.
I need to try.
So yeah, 1 meter as well.
Where's the line here?
Yeah, around here. Yeah. Ooh, maybe try again here.
One more.
Yeah, 2 tries. It's like 60. Yeah. You also this time let's try 2 meters. I think around here. Yeah, around here. Maybe around here. Yeah. Yeah, that should be good. Yeah. It's a bit harder then. Ooh, 50. Oh, that's great. Yeah. Let's do 2 meters as well. Yeah. Ooh, maybe another try. Yeah. Here. Ooh, I think that's like 50. Yeah, that'd be good. Wait, how many? Five or four? Ooh, let's go. Yeah, 2 meters as well, right? Wait. It's way further than that. I think around here. Yeah, around here. Ooh, that's like 60. Yeah. Great shot, man. Hey, Long, can you? Yeah. You have to. Yeah. Let's see. Okay, now we need like 3 meters, so like extra hard. I think around here. Yeah, let's do this around here. Yeah. I mean, we don't want anomalies, you know. Oh, that's a good one. Clean. That's an anomaly right there. Uh, 30. Yeah, 30. Yeah, we need few more. So Long, can you like 2 more? Yeah. Yeah, let's go. Yeah, 3 meters. Oh, it's not. We're doing like extra hard. So if you're up, yeah. Ooh, that's like 50. Yeah, 60. Let's do 60. Yeah, let's say 60. Yeah. Yeah, 3 meters as well. So like, yeah, that's it. Ooh, that was like what, 10 or yeah, let's say 10. Ooh, nice try though. Yeah, at least, yeah. 0. Yeah, can you? Actually, around here, yes. Ooh, I think 0 as well. Yeah, you'll be the last one today. Ooh, I think it's 10. It's just lighting. Yeah, let's make it 10. So, yeah. Thank you everyone for volunteering. Yeah. We will show you guys like an example of how like, we collect data and then build a linear regression model like in a real world problem. Nice one. Mm. So here are all of the libraries we're going to use today. And we have pandas, numpy, it's crucial in every machine learning project. And we'll be importing linear regression and train test bit as well. As I said before, the same in every machine learning project. And of course, matplotlib, which is commonly called PLT for some reason. I mean, yeah. So, what you doing? So as you can see here, there'll be, these are all the collected data, which we collected from people throwing darts. And we collected from like 3 levels, like 1 meters in front of the dartboard, 2 meters and 3 meters and so on. And other than that, those are the other ones are, which to save time is the mock data which we made to, yeah, to balance it out, just like that. Yeah. And here we combine the both data and convert it to a data frame. So here we'll be plotting all the data that we collected. First, the mock data, and here, as you can see, it's like a scatter plot. We're using matplotlib to like customize the labels and title, legend, and yeah, as you can see here, there's like clearly a trend, right? It's like a line like going down. Yeah. And here we're just printing the data frame just to check. Yeah. And here, oh, here, so we split our everything we collected into X and Y, which X is like the X-axis, which is the distance from the board, and Y would be the score, and the Y-axis. So here we do the splitting, the actual splitting, and we split into X train and X test and Y train to Y test to a proportion of 0.2, which means there is 20% will be test data and 80% will be train data and random data as well, just to keep everything balanced. And here's where all the magic works. So we'll be importing linear regression, and I know we taught a lot about like all the theory and stuff, but in Python it's actually just like one line, which is helpful, I guess. And I mean, same as before, model.fit is where all that training data happens, and yeah, just in one line. And here's how you actually predict. And we're predicting the X test, which we have split it from before. And we call this Y pred for predictions. And over here, we're starting to evaluate the model, and we're using MSE as our metrics, which result in 340. Pretty good, I guess. Yeah. And over here is the final plot. So it's the same as before, but the only thing difference is we're actually making a new line on top of our scatter plot, and it's only the test as well. So as you can see here, or from before, it's like we seeing a trend here, right? And now we're just putting a label. We just putting a line on top of everything. So yeah, that's pretty much how you create a linear regression model. And the key takeaway from this is that imagine you're standing 3 meters from the dartboard, right? And you'll be likely to get around 40, 45 for the points. So I mean, there of course there would be like some anomalies, but on average, you'll be pretty likely for you to hit like 40 or 45. Yeah, that's it. Thank you, everyone.
We'll now, from this point with classification, refer to this function more so as a classifier. Inputs get put in, or a select, as we learned last time, it can be a list of features being put in, and it will give us an output of a class. So our output is a label that we have made for the model to use. So yeah, we now call this model a classifier. So into a bit of the etymology behind it, or the naming choice behind it, you're basically getting a how does this keep happening? Can people mute us? Do you reckon that's like a thing? Yeah, let's figure that out. So because we're seeing, yeah, because I think people are we're being muted. Yeah, okay. Yeah, I think it's permission thing. Okay, yeah, sure, yeah. Huh?
Just continue.
Right. Anyways. So yeah, the key thing to note with the classifier and classification in general is that it will output a discrete value. So there's no in between. Say for this example here, our features or inputs are spam messages, spam emails, and our classifier has been trained to put these emails under 2 different labels of inbox. So it means it's a good email, and spam folder. So it's a bad one. So well, let's say, for instance, this model is looking at different words in each email or a link or the grammar, and it will then classify them into one of these 2 classes. So a quick thing to just kind of have a reminder on about these 2 classes. This example right here is an example of binary classification, where it's either one or the other. So it's sort of like a binary bit. It's 0 or 1 or the other. So both classification and regression can be visualized on a graph, but sort of how the data is being laid out is what the key difference is. Like with regression, you're seeing lots of data points that sort of amble around the general like look of a line. Whereas with classification, we're seeing like big groups, big clusters that all share like the similar value with slight permutations, some slightly different characteristics, but they all come under a set class. So you can have right here, you're seeing one class here and another right here. So again, we have two main types of classification. There's binary classification, where again, it's like a bit, it's there or it's not. It's this label or that label, this or that. So with my first example, you may remember I bought a lot of fruit, a lot of apples and a lot of bananas. Did I buy that just for this lecture? Yes, but it was really well, they tasted so good. And our classes were apple and banana. So let's say apple represented a binary output of 0 and banana represented an output of 1. Another label that we can use, say we wanted to focus on only attaining an apple. Another example of labels we can have would be apple and not apple, which say we get another fruit that is neither an apple or banana, they would all go into the not apple class, which is more helpful, I understand, if you're doing specifically binary classification and choosing to not have any more classes. So see here, this right here is a wonderful example of binary classification. Our model here is taking these images all as inputs, and it's determining whether they're a chihuahua or a muffin. Yeah, that's pretty wonderful, actually. That's also adorable. So, yeah. And then we also have on this right side multi-class classification, where we have 3 or more different classes, 3 or more different labels that our model is using to put data in. So you may start with a binary classification only having 2 classes, but then you may see a correlation in between a small subset of a class, and you may want to up the amount of labels you use and add a higher degree of specialization. Does anyone have any questions so far? On the chat as well. Feel free to type them in, of course, at any point. So here's a piece of data. Let's run through this graph very, very slowly. We have a continuous X input. So X can be any size of diameter in centimeters, and it gets represented along this graph. But we only actually have 2 outputs for our Y-axis here. So we have tumor size and whether or not it's malignant. So yes, it's a malignant will be represented by 1, and no is 0. So they've taken in data from a spreadsheet, and it will have the feature of diameter and another feature which will be the output we're measuring being malignant. With a straight line, we're not really capturing any sort of correlation or regression. To an untrained eye, we can probably tell that after a certain size and diameter, it's more likely that it will become a malignant tumor. So using a linear regression doesn't really speak to the in-between right here. You can't really have a 0.5 in between these two. So a linear regression cannot represent should not represent these discrete values, because having a 0.5 means what? That you either got a tumor that's malignant or it's non-malignant. It doesn't make any sense. So we look through and find a certain threshold in our y-axis that represent the cutoff point between 2 classes. So so let's say our threshold is 0.5 as a matter of fact. This is how we're going to be using a linear regression, or a line even, to then identify what we call a logistic regression. Logistic regressions are solely catered towards classification, and we'll go into that in a couple slides later. Any questions so far? So once we find a threshold, it will compare the like height and whatnot, whether or not it's malignant, and then it will determine a class based on that. So let's say with our function that we use, if we have an output that's less than 0.5, we'll round that down to a 0, so meaning it would be not malignant. If it's above, it would round up to 1. Once we have a threshold, so let's break it down on a whiteboard. This is a lot of lines and arrows and numbers here, so I think breaking it down is only appropriate. So we have one kind of input. We can already tell that this is a class of its own, and another. And there are only 2 values for the y, nothing more, nothing less, 0 and 1. There is no in between that you can access here. And we are drawing a linear regression. We can then look for a threshold we want to make, that like a cutoff point between 2 classes. So that can be where 0.5 would be. And once we're there, we actually can derive an x value for which that cutoff point exists. Now we can see if, depending on tumor diameter, whether or not it would be malignant or not. So yeah, it would look at the x value. It would derive what x value will change the value. Will change our output depending on the feature. Let's say now look at this example here. Let me go full screen. We're actually seeing an outlier here. So outliers can exist in our data where we have an abnormally, or sometimes maybe with research, maybe normally, high or out there value for one of our feature inputs. So right here we have a very high diameter, which can still represent where our this part of the class as well. But if we choose to include this feature and not accept it as an anomaly, it will actually affect the linear regression we draw because a different weight and a different bias will be used. And again, going to just illustrate this. So we have one really out here. A linear regression model we may make can account for this out there value and shift along that regression. And that in turn, when we still use the same threshold, will create a different X value point and a different cutoff point entirely. So these 2 X values here may actually be grouped with these circle values and will be wrongly classified. So accounting for anomalies and noise in data, as a brief description, noise means like messy, uncorrelated data that you can find in a database sometimes. So figuring out how to account for those can be very important as well. Oh. Okay. So once we have derived our X value, which will be a cutoff point, a threshold in between each discrete value along the y-axis, we actually get what is called a logistic regression. I mentioned it prior. A logistic regression will look something a little like this, like a sort of curvy, like snaking shape right here. And as you can see, it much better represents the distinction between these 2 classes, much better. Do you log both X and Y or just use one? Let's look at the chats. I think I don't know if we use logarithm for it. I believe it's derived from the threshold and the X point we use there, but we actually use a specific function to perform what we call the sigmoid function to form a sigmoid curve. This right here is called a sigmoid curve. So I'll just show you briefly. We have a lot of equations right here. A logistic regression, so y equals mx plus c, is not going to cut it simply for this piece of data. We've got to do something a bit more. So think it's important to illustrate this all out. We got a lot of information coming up, but I hope it won't overload. And if you have any questions, feel free to put your hand up as I'm presenting, or if you've got a question in the chat. Our prior function that we used last time, where we have f using a vector w holding all our weights and bias b of vector x. That used to represent our linear regression. Now we're going to be using this function to denote our logistic regression. So let's say we have a variable which is going to store a logistic regression we made at the start, where we had that line, a straight line being drawn. Let's say we have a variable z, which is going to store that vector multiplication right here. Now we're going to be calling another function or another equation. So you saw that squiggly line we made to the sigmoid curve. It can actually be computed, well, generically by this here equation. So let's say a is our function is equal to 1 over 1 plus e to the negative x. You'll not have to actually calculate this mandatory. It's not calculated manually. This is more the logic behind it that I'm going to be teaching, the arithmetic. So if you remember from last time, just going to illustrate again. Let's say, okay, x vector has all of our features we want to use. It's important. If anyone wants all of this on a whiteboard, more neatly structured, I actually have this, and you can ask for it, and I can maybe email it across if that's helpful for you. But this is a more step-by-step approach. And if you want to go over it again afterwards, of course, you can always call me over and I can help. Again, we have our weights vector, W1, all the way through to Wn, and they get multiplied as we saw last time. And then, so this variable z will store our linear regression. Now we're going to be calling another function. Let's say we have a function g, and g is calling z. So g is going to use a linear regression, and it will be this equation right here, 1 over 1 plus e to the minus z. So now what we're essentially calling is this. So we still have that linear regression equation. It's just an extra step being put through another function, which will give us a sigmoid curve. So the presence of distinct classes allows for the calculation of if an input fits in a specific class through probability at times as well. So as we can see here, this capital P denotes probability. So it will actually look at probability across as you go along the graph. But a key thing to highlight is that the probability of one record, one input being a class, when all the classes are being added up, the probability of all those classes being added up will always be 1. So it will always fit into one class. Another thing as well, someone's waiting in the lobby. Okay. Another thing to note as well is that when we get given a decimal value after we put in one input, it can actually, it will denote this probability. So if we get like a 0.7, that will be like 70% chance that Y is 1 or Y input is malignant. So the decision boundary that we just saw, where it's like 70% chance you round up or down. So it's like rounding up and down to give our discrete value. So our function obviously won't always output 0 or 1. We're using our boundaries and our threshold to denote to move up or move down on our graph where new inputs are being made so they fit into a specific class. So yeah, as I saw here, this being broken down again, we have our z equals, well, in this instance, it's got one feature, so one weight and one feature, whereas where I showed you earlier, I accounted for a vector of features and weights plus a bias, and this linear regression gets put through a sigmoid function right here. Now, a key thing to note, there are two key terms when we look at finding a good model. We don't just look at model accuracy and try to measure that, let's say through regression with gradient descent algorithms. A key thing to note is you should also look at and discuss amongst yourselves when you're making a model what features are important to be included and regularizing them. So how important is each feature? So adjusting their weights. As you see right here, we have a very clear curve in our data, and what this regression is showing us is a linear regression. We got one weight, one bias, one feature, and it just creates a single line, a straight line. This doesn't capture our data quite how we want it to. It's very simple. It's very lazy. Right here, we actually have a good fit, which uses a different function. So we actually are accounting for two different features. They each have their own weights. One of them is being squared to give us a curve shape. I'm sure maybe some practice on Desmos with like squaring your function as well can sort of better illustrate how these curves are made in a function. But yeah, it does well to generalize our data so that when we get given new data in a regression, it can go along this line that's being kind of perfectly well tuned. Whereas with an overfit, this is where we've actually gone too overboard. We've chosen too many features, upped the ante on too many weights. Maybe we've got the wrong bias as well. But while it is getting every single data point right here, the problem is that it's not actually finding a pattern. It's just memorizing each data point. So it might turn out successful for training data because it knows where everything is. It can memorize it. But when it's asked to put in new data, it will be like, oh, well, it must go here, right? Surely that doesn't really follow the general line of the curve here. So it's too complex. We've got too many features, and it actually learns more from the noise. Just memorizes everything. Now onto the underfitting, overfitting, and good fit example with classification. A very high bias right here against these two features being measured against each other. I can clearly see a class and another class surrounding it. And again, not many features being used, not many weights, and it's got like a very lazily drawn straight line. Whereas with this one, this looks like it's using a lot of different weights and squaring some of the features too. And at one point here, you're seeing now one feature being multiplied by another. The significance of that can be depending on the data set you're given. They may come up. Say, for instance, you actually have like a candidate key who here knows more about databases and data analysis. Right, so you may find in the database you actually have a candidate key or a composite key where like a value. Oh, someone put their hand up, lovely. Where two fields of data in a data set will come together to form a new value. So they'd multiplied most likely here. But yeah, it's generalizing our group right here quite nicely. You can see that there are two outliers here, but it's but there's only two. It's very likely that you're going to get crosses, new crossing generated into or identified here, and circles on the outside. Whereas with this one, it's gone very overboard. It's going to instantiate. It's going to assert that just because they've memorized a circle being here or one class being here, they will only be circle classes being put here, which doesn't really follow along. If you look at it with an untrained eye, you can kind of just see that these are very much outliers or noise in our data, but it will still like draw around it with a very, very complex function we don't really want. So it captures this again as a noise. It captures this noise and instead will actually predict whatever comes into these small pockets to be circles. So how do we solve it? We actually have to address this problem of overfitting our data because, again, it will only work for the training set we give, not for any test sets that we generate, not for any new sets that come in because they'll just give us an inaccurate claim. So we have two different options we can select here: feature selection and regularization. So look at this little example here. We actually have X1 going all the way up to X100. We have 100 different features being used. And some of them aren't even relevant, but if you apply a weight to them, they actually can affect your data. So right here, again, as we saw previously, too many features and weights makes for a complex model that overfits, tries to do too much for its training data. Like these five first features are very important. The size of the house, how many bedrooms, how many floors, the age of the house, and income as well, can actually be all very poignant factors in determining, say, house price. Distance to Tesco does absolutely nothing. You shouldn't include that ever, I don't think. So yeah, many features, but little training data should not leave you room to start putting in distance from Tesco. But let's say now, say we want to, because we can still end up with an overfit after what is called regularization. Regularization looks at the weights of each feature. So say we want to keep all our features. Say for whatever reason you want to keep distance from Tesco, don't know why. These numbers are massive. 28, 365 by something squared can lead to large values, and that can be computationally expensive to calculate and also difficult to write because there's also a practicality aspect. Say as a tenant of a house or no a landlord, you're going to look at house prices. You don't want to look at big numbers all the time. So with regularization, it will reduce the weights, scale them down, and actually affect each weight and tweak them. Say here, this first feature here has been scaled down by like a factor of a half. This one has been scaled down massively right here. So from that, we can actually gain that this feature was not supposed to be as important. So through the process of regularization, tweaking the different weights, we can actually gain a new, a much more refined and smaller scale model as well. Now, I think this is the last slide, but there's one thing I quickly wanted to go over on the whiteboard. Yes, I hesitated to actually bring this up in our last lecture because the notation and word I'm about to use actually applies much more and is used much more with binary classification than it is with linear regression. So look here again. We have our vectors for weights and inputs. And you can obviously draw that along like this. We have input 1, input 2, spanning all the way down to input n. And they're going to get put for a function. So we have our function that takes in a vector of weights and a bias, and our vector of inputs, and gives us a y. And obviously, each of these features get put through this function, and they get multiplied by their each unique weight. So W of n, W of 2, W of 1. I hesitated to use this word and this exciting development here for regression. But this right here is, in essence, an example of the most simple neural network we have. What we actually have right here is something taking in a set amount of inputs, making a judgment based on mathematical and statistical evaluations, and giving us an output. That, in effect, is a neural network. And the term for this very, very basic neural network where features get multiplied by weights put for a function is called a perceptron. If you want to do more research on this in your own time, you're more than welcome to. I think the topic, in my opinion, of neural networks in general can be quite top heavy, and we don't want to overload your brain. And obviously, we don't have much time left either. But yes, this is, in effect, a very, very basic neural network, which I think is very exciting. Yeah, I think that's it for this lecture. Thank you so much for coming. Thanks so much for attending online as well. And yeah, if you're wanting to move on to the labs,